this kind of scheme. You see that the scheme becomes more complicated because you don't have one linear reservoir, but you have many. Each subunit of the catchment must be characterized with its own K value, the constant of the linear reservoir, and a value of W max. So you have to define a lot of parameters. These are parameters. The maximum possible value for W and the constant of each reservoir. They are parameters. Must be defined in each subunit. And therefore you see that it becomes complicated, the process. The model becomes complicated. You can imagine that the computational requirements increase. And also you can imagine that you may have some problem with defining these parameters. You need a lot of information, local meaning at each subunit you need information. Because if you want to define the water storage in a physically reasonable way, you have to make the water storage consistent with soil type at local scale, geology at local scale, etc. If you have impervious areas which are not permeable, then you have to define them by setting W max to 0. So you need information, you need land use maps, etc. Okay, but this is a possibility, and this would be a spatially distributed model. I'm not going into the details, it's just a descriptive mention that I would like to make. And I also would like to make clear that the literature proposes different shapes for these subunits. In this case, I used a rectangular grid. There are some models that use a triangular grid. There are models that subdivide accordingly to sub-catchments. In any case, if you want an accurate description, these units must be small. Like maximum area of 1 square kilometers. 1 square kilometer, which means if you use a rectangular grid, maybe 1 kilometer per 1 kilometer. So if it is, it's a small size, but still too large, too coarse to define heterogeneity accurately. Because unfortunately in hydrology we have soil properties that vary from year to year. If you move 30 centimeters, when we try to measure infiltration, we put the instrument here and we get a water storage capacity which is different with respect to the one that you get if you move half a meter apart. Okay, this is a possibility then, but let me illustrate with more details a second possibility, which is based not on a deterministic description of the water storage in each area, each side of the catchment. This is a deterministic description, meaning that I define in a deterministic way the water storage with no uncertainty. Maybe that uncertainty is related to the measurements that I take, but for the position, it's a deterministic representation. So for each position, I define water storage. Let me mention and turn to a statistical description. Because indeed, if I'm interested in modeling the river discharge at the catchment outlet, I am interested in getting the amount of the saturated area, but I'm not strictly interested in knowing where it is located. Of course, it's a useful information to know where it is located, because if I want to transfer the contribution to the outlet, It's a useful information, but I don't strictly need it. I need the amount of the area, but not really. So if I got a description of the amount of the saturated area without knowing the position would be enough for me. So I can try with a statistical description. And what kind of description could I use? What is the information that I need? I would need an information that, depending on rainfall, tells me what is the percentage of the catchment area that is saturated. This would be enough. So I know that it rained 10 millimeters of water. If I have a relationship that tells me what is the percentage of the catchment area that is saturated, this would be enough. I say the percentage just because I like to speak in adimensional terms. I could say that the amount of the catchment area that is saturated is the same thing, but I would like to speak about percentage because it's more general. So again, if I had a relationship telling me, depending on rainfall, what is the percentage of the catchment area that is saturated, I would be satisfied. So let me try to depict this relationship. So let's write in a graph varying from 0 to 1 in the abscissa, in the ordinates, sorry. I visualize on the y-axis the percentage of saturated catchment area. So let me call this F, which depends on, of course, on rainfall, but I don't want to use a symbol for rainfall now, because I have to stay more general. Let me put a quantity C, which depends in turn on time. Let's think about rainfall, but I use a different symbol because you will understand why. I can't put rainfall there. You will understand why. But let's think about rainfall. Rainfall depends on T, time, and determines this percentage of saturated catchment area. And let me put this quantity C here. And now I have to be more explicit on the meaning of this C, which of course is related to rainfall, because what determines the saturation of the catchment is rainfall. No doubt. But I can't use rainfall for two reasons. First, there is a very easy reason why I can't use just rainfall. Because I have evaporation. So if I have a strong evaporation, I need more rainfall to saturate the catchment. Given that I need here a one-to-one relationship, the presence of evaporation doesn't allow me to use rainfall as independent variable. At least I should subtract evaporation from rainfall. But it means that I can't use rainfall, so I can't say rainfall. This is a first reason, which is easy to understand. And also there is a second reason, which is mathematical, that explains again why I can't use rainfall. Because, you know, after saturation, complete saturation of the catchment, even if I have an increase of rainfall, the quantity F doesn't exceed 1. It is limited to 1, of course. So if I use the rainfall, this relationship wouldn't be so, would be a relationship that as a mathematical form that is complicated, because I have to change the shape of this relationship when I get to 1. Instead, I want to use a mathematical relationship that is easily tractable in analytical terms. So how can we define C? Let's define C as the water storage expressed in the dimension of length, so millimeters. And I have to say this because if I say water storage, one thinks at the volume. Instead, I am talking about a volume per unit area. So when I say in this case water storage, I mean a volume per unit area, so an height. So C is again the water storage, not rainfall, water storage in the areas that are not saturated. Again, because this is an issue that I want to make sure that is clear to you. I have to distinguish between the areas that are saturated, for which the water storage is the maximum, and the areas which are not saturated, in which I still have a change in the water storage. So I need to refer to water storage in areas that are not saturated, and this is C, where the water storage is expressed per unit area. So how can I compute this water storage then? How can I compute C? Simply, I have to take rainfall, cumulative rainfall from the beginning of the event, subtract evaporation, evapotranspiration, and make sure that the area is not saturated. Then this is the value of C. Please note that this procedure is not valid for an area that is saturated, because in an area that is saturated, the water storage is equal to the maximum. It doesn't depend on rainfall anymore. Okay, this is the reason why I have to make this difference. And I hope the concept is clear. So let's compute C in this way. Rainfall minus evapotranspiration. And this is valid only if you are over an area that is not saturated. Now, my relationship then, first of all, C is limited between 0, we are talking about the water storage cannot be negative, and what? A quantity that I call C max, which is the maximum water storage over the catchment. If you get the individual point, infinitesimal area, where you have the maximum water storage, you measure it, and this is C max. And then, of course, I know that this relationship that I'm looking for should pass through this point, which is C max 1. When you get a water storage in an area that is not saturated, which is equal to C max, that is the maximum water storage over the catchment, you are sure that your catchment is saturated as a whole, is completely saturated. The percentage of the area that is saturated is 1. Let's assume also that this relationship passes from 0. This is not necessary. It passes from 0 only if you have some impervious areas. Or let's say an infinitesimal impervious area. So let's assume that it passes from 0. And then we have to find a relationship connecting these 2 points that describe, again, the percentage of saturated area in the catchment depending on the water storage in the catchment itself. And this relationship, of course, can be linear. But let me now introduce the model I'm talking about. Now I am passing from the general class of the variable contributing area models to a specific model, which is because, of course, models differ for the shape of this relationship. And the model that I'm talking about now is called I mod. Is written, I think, in this way with the capital M and capital H, but it doesn't, let's say I mod, it doesn't matter if you write in lowercase or capital letters, it's not a problem. And I think it is a very useful model because it's very flexible and very simple. Because you will see that the behavior of this model, which is interesting, is that in order to explain it to you, I will have to fill 3 black boxes of formulas. But when you go to the PC and you apply it, it's just a few lines of program. Very simple to apply. It's very simple to apply. It's more difficult to understand. But you know, I think it's better in this case than the opposite. It would be, we are engineers, so we are looking for flexible and easy to apply solutions. The theory doesn't concern us, more or less. After the exam is not concerning. Okay? So, this is the model I mod, and of course a distinguishing feature of the model is the form of this relationship. And let me write it down. So let me write FCT a colleague that is working in Greece, I'm opening a parenthesis just to relax a bit, told me that now the UNI rules allows us officially to open multiple round parentheses. So if you look at my notes, you will find in the slides that I use the square parenthesis here. While now I'm dropping the square and I'm using a double round, because I think that it's easier for me to teach, because by using different type of parentheses you may make a mistake when you write it down. So in this case you will find this difference. I'm using round parentheses here and square parentheses on the slides, and I decided to do so because this colleague of mine told me that now you can use it, because we wrote a kind of contribution to a journal, and I was using the square parentheses and also the graph, I don't know how to say in English, and he told me, no, this notation is no more modern, it's old-fashioned, we have to be. And he mentioned to me that the UNI rules now allows you to open an infinite number of round parentheses and suggest not to use square parentheses anymore. Anyway, this is just for fun. Okay, so let me define now this relationship, where again, please don't forget the meaning of f, which is a percentage varying between 0 and 1. So, let's write in this way, 1 minus Ct over Cmax to the power of beta. This is the relationship. Beta is a parameter, and Cmax is a parameter as well. So we already introduced 2 parameters, which depend on the catchment, of course. Now let's look at the shape of this relationship. And let's first of all assume, we have to assume a value for beta if we want to study the shape of the relationship. Let's assume that beta is equal to 1. Then if beta is equal to 1, you get 1 minus 1 plus Ct over Cmax. It's a linear relationship. So we can connect these 2 points with a straight line and say that corresponds to beta equal 1. Now, study what happens if beta is equal to 0. So let me write it down. Beta equal to 0. We get F Ct equal to 1 minus 1 beta equal to 0 means that the quantity between parentheses becomes equal to 1. So 1 minus 1 equals 0. So what is the percentage of the saturated area? Is 0. Until I get to Cmax. So if I wanted to write here, I would need to write in this way. This is beta equal to 0. This is a limiting case, which is the case of the linear reservoir. For the linear reservoir, until you get to, not the linear, let's say to the reservoir, until you get a value of Cmax, you have a percentage of saturated area that is 0. And you get this situation if you add the water storage capacity over the catchment that is constant and equal to Cmax. Okay. Now, what happens if you have beta equal to infinity? I write here beta equal to infinity. Let's say not equal to infinity is not correct, tending to infinity. Then we get F C T tending to 1 minus what? Let's look at the quantity between parentheses. It's a number that is lower than 1. The quantity between parentheses is bounded by 0 and 1. Because if you have CTT equal to 0, then you get inside parentheses 1. If you get CTT equal to Cmax, the maximum value, you have inside parentheses 0. It means that inside parentheses you have a quantity that is in general lower than 1. Okay? And therefore, after the starting of the event, and therefore, if it is lower than 1, if you raise to the power of infinity, you tend to 0. So 1 minus 0. It means that F tends to 1. Therefore, if I wanted to draw here the result, it's like so, which corresponds to the situation of impervious catchment. This is beta tending to infinity. The typical situation that we get in catchments, in real catchments, is given by a curve that corresponds to beta between 0 and 1. Okay, now, at this point we have quite clear what is the shape of this relationship that we were looking for. Now, we have to ask ourselves how the river discharge can be computed. Because at this point, if we knew rainfall and if we knew evapotranspiration, we would be able to estimate what is the percentage of the saturated area. What is the percentage of the area such that water rained over there is transformed in river discharge. Remember the first assumption. Only saturated area induce river discharge. So, if I knew the percentage of the saturated area, I would be able to say that rains that falls over that saturated area is transformed in river discharge. Okay, good. So, how can we compute then river discharge? Basically, what we have to do is to compare the value of Ct with the volume of water that is stored in the catchment. Because basically what is Ct? Ct is net rainfall. Is rainfall minus evapotranspiration. But part of that net rainfall is stored in the catchment. It is the rain that fell over the unsaturated area, is stored in the catchment. Instead, I'm interested in knowing what is the amount of water that was not stored in the catchment, because it is river discharge. So I have to subtract from Ct the value of water that was stored in the catchment. So the amount of rainfall that fell over unsaturated areas. So basically, I have to estimate the difference Ct minus Wt, where W is water storage over the catchment, which is lower than Ct, because Ct is net rainfall. Let's think about rainfall for simplicity. Why? This is water stored, and the water was stored only if it fell over an unsaturated area. So I have to compute this Wt. And how can we compute it? Of course, we can write that Wt is equal to Ct minus something, which is the amount of water that was not stored because it was transformed in river discharge. Minus something. What is this something? Now, I wanted to make clear to you in the next 5 minutes that this something is given by the integral between 0 and Ct of f c tau f tau, sorry, in the tau. I want to make this clear. So far it's not clear. Where f is our relationship here, which is given by the relationship that I raised on the blackboard but was written there. Okay. Now, why this? Why why the water that was rejected by the catchment, so the water that I observed as river discharge, is given by this integral. Now, this is a critical point for the understanding of this model. I would say the last one. And I write again this graph here, because I want a clean graph. And so this is F Ct. Here I wrote F tau because it's the variable of integration. And this is Ct. And let me write, let's assume that it has this shape. So this is 1, and this is C max. And let's suppose that we are at a certain time instant in which I have a value of C star t. And let me assume that if I increment the time infinitesimally, I get a value here, C star t plus delta C. So let's say that at this time instant, I have an increment of Ct, which is given by delta C, which of course I can draw here. And this increment of C means that it rained something over the catchment. And of course the increment is given by the amount of rain minus evapotranspiration. But if I have an increment, it means that effectively I have water, net rainfall, falling over the catchment. Net rainfall. Part of this net rainfall, of course, is infiltrated, because it falls over unsaturated areas. But of course, part of this rainfall is rejected because falls over saturated area. Now, at this point, Ct, I have a percentage of saturated area which is given by F C star T. Of course, if it is, let's say, 20%, it means that if I multiply delta C, which is net rainfall, times 20% of the area that is saturated, I get an estimate of the amount of rejected water. And this is the product. Of course, you see, there is, if the increment is infinitesimal, this approximation here, which comes from the increase of F due to the increased delta C is a second order infinitesimal. I can neglect it. Okay? Because the amount of rejected water would be not given by this rectangle here, but given by also this triangle here, which is a second order infinitesimal. Because the increment delta C is infinitesimal, and therefore I can neglect it. Therefore, you see that if I start this operation from the beginning of the event, because this rectangle is just the amount of water that was rejected by the catchment passing from C star to C star plus delta C. If I extend this operation from the beginning of the event until C star or C star plus delta C is the same, I get the integral of what? The integral of F. So the estimate of the rejected water from the beginning of the rainfall event, indeed, is given by the integral of f. And I hope this sufficient to make it clear why here I wrote the integral of f to mean the amount of rejected water. Now we have to compute the integral, but it's not the big problem to compute the integral. The problem might be to get the concept, and I hope I was clear enough to deliver the concept. Okay, so my next step would be now to compute the integral. And any questions so far? Okay. So I think I can delete this. And what I need now is to substitute here the expression for f that I gave to you before. So I'm writing below here, just by substituting for f its expression that you have. So Wt